Hello everybody, welcome back. Today I would like to do some more embedded Rust coding. I'd like to continue where we left off last time with the rotary encoder. What we did was we had a rotary encoder that would increase or decrease a value. So let me show you where we ended up. We flash it, we run it. And then it was running like this, and when I rotate that knob, it would change a value. And so now it's increasing, and then I rotate back, then it's decreasing, and then it gets negative, etc. So that's what we did last time. So now I would like to control a stepper motor with it. So I have a stepper motor here. I did the stepper motor before. That was a really small unipolar one. This is a bipolar stepper motor, quite a bit beefier and more powerful. I put on a cloth bag to make sure that if it moves that it's easier to see. But the difference here is that you actually need a certain kind of motor controller. Well, you need it in the last one as well, but it's a different kind. And the one I'm having here is this one, TMC2208. This is a so-called silent stepper, and they're called silent. I mean, the controllers are always silent, but a stepper motor basically works in sort of pulses. So every time you pulse, the motor rotates a little bit. But if you think about it, that can be a pretty noisy thing. It's like turning your motor by hitting it with a hammer. It's really sharp, and you can look on YouTube or something like that and look for like a stepper motor orchestra, because basically it's a speaker. If you pulse it at a certain frequency, that's what will what the sound will be. The silent steppers are better in the sense that they really ease in and ease out the power. So the steps are much softer. It's like hitting it with a soft hammer, basically. So these are really nice. Pin wise, they're compatible with like this one, the A14988, which I think it should do basically the same, but it doesn't have the smoothness. But it's quite a bit cheaper, and depending on your use case, it might not matter at all. So yeah, they're largely interchangeable aside from that. So how do you wire those? Let's have a look. So these are the pins. These M1 and M2 are the coils to the motor. So the motor has a connector that just fits on that. Pretty straightforward. And then you have the power to the motor. And then you have the connection of the power for the logic. It's important not to confuse the two, right? They can have wildly different voltages, and definitely quite a lot different in the power draw. On the other side, there are a bunch of things that we're going to ignore now. You can use that to configure certain things and to basically customize how that is supposed to work, but that's out of scope for now. This one is important, enable. If you pull that low, so you connect it to the ground, then the controller will power up. If you don't, then it will power down. So right now I haven't done anything with it. I just hardwired it to low, so it's always powered up. But if a stepper motor is powered but not moving, it's actually holding its place, right? If you try to move it, it really will resist that. But that also means that it's using power, that it's slowly getting warmer and warmer. So depending on your use case, you might want to, whenever you not actually moving the motor, just don't pull the enable high, and then it will just not use power there. The actual controller is with these two, direction and step. The first one, direction, is high, or if it's high it moves one way, if it's low it moves the other way, and step is just a step. So that's the one we will keep on toggling every so many microseconds, and then it will do its thing, right? So we are just if we want to move it 1,000 steps one way, we toggle it 1,000 times. Yeah, that's it for here. So let me show you what I made of it with questionable wiring. So I moved the encoder up a little bit, but the wiring is identical. I didn't change it at all. So this is the motor controller. These are the step and the direction pins wired to pin 1 and 2. This is the motor. That's this one, the same wire. This is the enable, so it's this wire that goes all the way here, and it goes to the oh, I'm kind of in the way. Well, let's move it a little bit. No, it's fine. So yeah, it goes to the minus of the logic voltage. So this rail, the plus and the minus are for the logic, and this one is for the motor. So I connected these two here to the logic power, and these two up here. Yeah, it's a flat wire. Oh, you can see it actually much better than I can. And this rail is going to a external power supply that powers the motor. So it is a bit hacky, but it is as straightforward as it gets, basically. So let's first see if we can get this motor to move at all. First of all, I would like to get back here. Yeah, let's get to coding. So let's get rid of the red blinking. It's annoying me. So we made the point that it still will keep working, so I'll just remove that. So it will actually be quite similar. So let's make an async function, and we call it just motor, and we call it pin. Now let's call it step pin, and that's GPIO1, I think. It's an output pin, and it's a push-pull. And then we have the direction pin, and that's GPIO2, and that's output, also push-pull. Yeah. Maybe I need to import something. And what's wrong here? GPIO1. Oh wait, Max messed up this one. Alrighty, I need to import this one as well. Okay, we need to annotate it with the embassy executor. So basically what we're going to do here, we're going to do a loop. We're going to toggle the step pin, and we're going to wait for a certain amount of time. So let's go to the step pin, and we do toggle, and we unwrap. That's a cause for complaining because it's not mutable. So let's make it mutable. Direction as well. We know we're going to change it. And then we need to wait. So let's do timer after duration from millis. Let's do 10 milliseconds and await it. Alright, so now we have an internal loop that will just spin the motor, right? Let's add it here. So we're going to do spawner spawn motor. That's pin 1 and pin 2, if I am not mistaken. We unwrap it. We need to make pin 1 and pin 2. These are push-pull outputs, is like pin 3. Copy, copy. 1, 2, and 1, 2. Okay. Let's see what that does. Let's give you a few. Something went wrong. The count still works, but the motor doesn't. But that's because it's not powered up. Still not doing anything. Let's see what went wrong. Did we actually do the toggle? Yeah, right. Step pin and the toggle pin. Let me have a look. Pin 1. I think I mixed them up. I think this is the direction pin and this is the step pin. Let's see where that leaves us. Oh yeah, it's moving. So, not fast, but it's definitely moving. But that's one of the nice parts of these stepper motors, right? They're really precise and they're actually quite powerful. I can hold it, but it is putting up a fight. And I even like put a lot less voltage than it can take. So it's nice that it has this kind of precision, right? So let's see if we delay a little bit less. Let's instead of 10 millis, let's do 1 and rebuild. And that's quite a bit quicker. Right? They're never like really fast. It's not like a drone motor or something like that. Not sure exactly. I think we can push it a little bit more. So then we have to go from micros and maybe 300. Let's see if it keeps on going. There's a limit to it. At some point, if it's faster than a certain, if it's too quick, then it will just stall basically. So now you see it's pretty quick, and only now it really start to make a sound, because before I couldn't hear it at all. So I guess we are pretty close to the max for this motor right now. So I will just power it down for a moment, so it's not heating up too much, because you can feel if you use it for a while it gets warm. Okay, so now we have the motor works. Now let's see if we can control the speed and direction from the rotary encoder. So for that, let's there are several ways of doing it. I think the most basic way, what we're going to do now, is just using a static variable, that an atomic variable that we can use for both sides. We can load and we can store to it, and then we can do that. I would like to try it with signals, which is a primitive from the MSC Sync. I might do that later, but for now, static. Let's call it delay. That's atomic I32. Let's do that. Is atomic I32, new, let's call it 0. So we have that. For the rotary, so right now what we did, where's the rotary? Yeah, the encoder is here. We had that count, right? This one. We could load it straight into the static we had, so like delay, and then we store it, and then we take count, and I think this is ordering, so I think like this one. You have to define how strict it needs to be in terms of atomic operations. Now in this case we know that it is a single threaded process to begin with. There are no other threads, it's just the async reactor. And also the encoder will only write and the motor will only read. So there is not really a lot of actual locking to do. So I think we can get totally away with using relax. So let me import that. This one I think. And then we need to unwrap it as no. What's the warning? Oh, I need to assign it to something. Yeah, that makes sense. Right? Okay, because outside the loop. Yeah. Fair enough. So we put it right here, and then it will store it here. What's wrong here? We need to do a semicolon here. So now we're storing it. And we'll need to, yeah, let's use this one, I32. Should be plenty. So now the rotary will store it, but this is not really a very useful number because we need to think about, first of all, we don't want to do a number, we want to have a delay. So the bigger the delay, the slower the motor is. And also we are encoding what I would like to do. If it's negative, it runs one way, and if it's positive, it runs the other way. But that's not how a delay works, right? The delay is delay. So we might need to do some pre-processing here. And I prefer to do it on this side because otherwise every pulse of the motor will recalculate it. Right? So what I would like to do is something like this. I would take like a big number, let's say 1 million. We are all talking microseconds now. And I'm gonna divide it by the count. So something like that. That kind of does work up to a point because like it but the resolution is pretty well, it takes a lot of turning to get anywhere. So what I would like to do here is just to take it to a power of 3. Right, so let something so somehow it's not auto-completing anymore. Let me restart the editor. That happens sometimes. So I would like the counter to have a bit quicker effect on the whole thing, right? So I do to the third power. It's better to do it to the third power. At first I tried to the second power, but then you lose if it's positive or negative because power of 2 will always be positive, right? So there are some other things to take into consideration. Right now, what did we create? It's I32, that's correct. We don't want to divide by 0. So if count is 0, which it is right at the beginning, then we don't really want to do that, right? So let's check for that. If count is not 0, then we do that thing, and then we can just load it in that case. So we just load this expression. If count is 0, I would still like to load it. So we can kind of model that the motor shouldn't be moving at all, even though like as a delay of 0 we don't want to actually do that, but at least we can indicate that. Okay, so that's the writing part towards atomic. This is a super crude way of doing it, and there are probably way nicer ways to control the speed. But let's get to the motor side. Right now we were just toggling, right? So first of all, let's load the delay. Is delay load, I think, and then I think we can do ordering relaxed again. And now we have a delay. So if the delay is 0, then that means that we don't want to, oh wait, we should put it in the loop, of course. So that means that we don't actually want the motor to move. So it doesn't mean that we don't want the delay, right? Because if you don't move but you also don't delay, you kind of block the whole reactor. So let's do that. If delay is 0, just don't do anything. We just do a timer after. It doesn't really matter. Some small duration from micros, let's say, I don't know, 1000. From millis, 1 is then nicer, but and I want to continue. So don't do the rest of the and await it. So it will not perform the rest of the loop, and it will just be idling here, right? So next thing, we need to check the direction, right? So if delay is bigger than 0, then we want to flip the direction pin one way and else the other way. So you probably can do this in a more compact format, but I kind of like to be this kind of verbose because it's easier to read in my opinion. So then we do a set high, for example, and unwrap, and we do direction set low and unwrap. So we encoded the direction, then we need to toggle, and then we need to delay for this period of time. So we do use the delay. This probably need to be casted to something, yeah. And obviously we need to do absolute value, because otherwise it might try to delay for a negative amount of time, and that's I'm not sure how the delay function will respond to that, but it's not gonna be useful. So we need to cast that also as U64. So this is done. I would like to add something else here, because I would like to limit what that delay can be. So we did all that. So if the delay gets extremely high, I don't know, millions, then this in the motor, this await will take really long, and no matter what you do with the rotary encoder, it will just freeze in place until that delay is over. So I think it makes sense to have an upper limit to it. And as I said before, there's also a lower limit to how short a delay can be, because if it gets shorter than that, the motor will just stall altogether. It will use a lot of power and might even burn up, who knows. So there is a limit, a reasonable limit to how quick a motor is supposed to run at all. So what we can do here is we can reuse the delay name, and then we take delay and we can do something like max. So that will return either the value of delay or some value, whichever is bigger. So for example, if I don't want it to ever run quicker than well, let's say not less than 50, then I can do 50. So then it's either the delay, or when it delay is lower than 50, it will return 50. So it's kind of a lower limit. And let's do also an upper limit. And then we say like it doesn't matter too much, but I don't know, how slow do you want to be able to go? So now we kind of limit it to that range, and that will make it behave a little bit better. Okay, let's see where we ended up. Okay, let's see. It doesn't seem to move. Let's figure that one out. Let's print something here. Let's see if the motor is actually trying to do something. Now let's do it after the delay so we can print it. It's the most basic way of debugging, but still does the job, right? Print lines. So it does seem to, I think it's just that I forgot to power on the motor again. Let's, yeah, there it goes. Yeah, it's always the easy things. Now that thing is messing up the output a little bit, but let's see. So if I start removing. Yeah, so it does kind of removed some granularity. But it's kind of nice, right? That you can just play with it like that. Go really slow. So yeah, there's obviously you can do a lot better job of making that really smooth, but it's pretty straightforward. All the actual embedded stuff of the programming is super easy. The wiring can be a little bit tricky. It's hard to debug when it's not working at all. Possible improvement could be that if the delay is 0, that we would bring up the enable pin so the motor shuts down instead of just holding into place. That might be an improvement you could do. Yeah, this whole scaling thing, what is it? This one, super basic. I guess there are better ways to do that. But yeah, it is a really straightforward code, and it's quite performant. And it's really nice that you can just add stuff, right? The whole encoder part, I mean, we added the transforming the count, but for the rest we didn't touch it, right? It's very modular. We don't need to touch other things a lot. So I like it. I'm pretty happy with this thing. Yeah, I hope you enjoyed. Let's play with it a little bit more. I hope you enjoyed. Please give me a like if you enjoyed it. If there is other stuff you would like to cover, I have still quite a backlog, but let me know anyway. And if I did something silly, I'm sorry, but please let me know, because it's interesting to have the conversation. And see you next time. Bye.